Okay, so welcome back. This is our fourth video about graph decomposition. And now we're going to discuss one important algorithm to us, that is the algorithm that converts one elimination order into a joint tree. So this algorithm is going to be important to us because it's going to give us a practical way to create joint trees. For now, we have assumed that the joint trees were given, so we created that in some way. We can create these joint trees by hand, just by analyzing the graph. For some structures or for some Markov networks, like the grid-shaped Markov networks, that's going to be easy because we can look at that and find a pattern like joining two variables into a cluster and create a joint tree from that structure. But for other networks that are not so structured, creating the joint trees is much less trivial. And this algorithm is going to give us a simple way to create the joint trees from an elimination order. So we can, you may think, well, but how do I create an elimination order? But we haven't seen many techniques in this lecture for doing that. So we can use the heuristics to create elimination order. We can use the prefix techniques to start with one optimal elimination order and use other techniques to complete that. So we have enough tools for creating elimination orders, but we don't have enough tools for creating a joint tree. So this part of the lecture will give us this tool. So one important feature here is that the algorithm is going to be polynomial time. So it's going to be easy to convert the elimination order into the joint tree, because if this algorithm it was like exponential time, it's going to be completely useless, right? Because it's going to take a large amount of time to convert one thing into another. So it's important to be an efficient algorithm, and it's going to be also width preserving. It means that the width that we have in the elimination order will be the same as the width of the joint tree. And the algorithm will have two parts. One is constructing the clusters, and we haven't seen this before. It's going to be the clusters of the elimination order. We just have to do a little bit of post-processing in those clusters in order to use them to build the joint tree. And the second part will be the assembly of the joint tree. It means that we're going to take these clusters together in some way in order to build a tree. And we're going to see two ways of doing this. One uses an iterative algorithm to iterate over the clusters and build the joint tree. And the second one, you use a maximum spanning tree in order to do that. So let's get started and see how those techniques work. The first part of the technique is to generate the clusters. We will start with a Bayesian network or a Markov network. In the case that we start with a Bayesian network like this, we're going to turn that Bayesian network into a Markov network by removing the directions of the edges and by modalizing the graph. So this is the modalized version of the graph. We call this also the iteration graph. The red edges, these two red edges, they are not created right away. They are created in the process of eliminating the variables and generating the clusters. We haven't seen this technique before, but I'm going to discuss this technique again because it's going to be useful to us. One important thing about the clusters is that they have two properties that are important. The first one is that they satisfy the first two conditions of the joint tree. So this part here, just remember that the first condition of the joint tree is that the cluster Ci is a set of the nodes in G. So this guy here is G, and we want that the cluster that we generate to be sets of nodes from the original graph. And that's going to happen. So I'm not sure if you remember when we discussed this technique, but we're going to revise this in the next slide. But every time that we eliminated one variable, we're going to create a cluster that are the neighbors of that variable. So yeah, basically the clusters will be a set of variables from the graph. And the second property of the joint tree is that each factor in the graph must appear in some node Ci. And we're going to see that is also true because when we eliminate the variables, we create clusters that are basically the multiplication of all factors that mention that variable. So naturally, the cluster will involve all the variables from all the factors that mention that variable, so we can associate the factors to that cluster. So it's going to be easier to understand this using one example. And the second property here is that the joint tree that we're going to generate will have the same width as the elimination order. So we'll create clusters that are smaller or equal to the width of the elimination order plus 1. So the width of the joint tree will be equal to the width of the elimination order. So this is one example that I mentioned that we haven't seen this before. It is the sequence of clusters generated by this graph here and this elimination order pi here. So we started by eliminating the variable f, and this will create this cluster C1 that mentions DEF. So why is that happening? Basically, this graph is telling us that in order to eliminate f, and reminded that in order to eliminate one variable, we needed to put together all the factors that mention that variable. So it's saying that there are factors that mention f, but are also mentioning variables d and e. So there is one or more factor with those variables in common. In fact, if we look here on the bottom, we see that we have this factor f, and this phi f here is mentioning the three variables d, e, and f. So in order to eliminate f, we will have to create one cluster first with d, e, f, and later on we're going to eliminate f and generate one factor that mentions only d and e. So this is the first step. In the second step, we will eliminate the variable a. And variable a is here, top of the graph. In order to eliminate a, we will have to create a cluster that also mentions variable b and c. So why is that happening? And if we look here, we see that we have this phi a here that mentions variable a, but also this phi b and also this phi c. So in order to eliminate a, we need to put together the factors that mention that variable. We're going to put phi a, phi b, and a, and phi c, ca together and multiply this. So we're going to eliminate the variable a, and we will generate a new factor that mentions b and c. And that's why we have this connection here, because this fill-in edge, like we call it, is basically the result of the elimination process, where a new factor will be generated connecting these two variables b and c together. We move on in the elimination process and go to variable b. When we eliminate the variable b, now I will have to create a new cluster that mentions b, c, and d. So we have this variable being eliminated, and we have these two neighbors here. And so there are factors that mention these three variables. And in order to eliminate the b, we will have to put this factor here inside here to be multiplied. But we say, well, it's just mentioning d and b. Where is the factor that mentions b and c? Is the factor that came from here. So we will need to multiply these two factors. This is not one of the regional factors that we have in the Bayesian network, but they will be generated during the elimination process. So we have to put this factor together. We created this cluster C3. And we move on, right? So we're going to eliminate the variable c. Variable c will have to put together factors that mention c, and they will include c, d, and e. So that will be the new cluster here. And we see that in fact we have this new we have this factor here that mentions variable a and c, and we may ask where is the factor that mentions c and d. And because this is red here, we know that it will be a factor that was generated during the elimination process. And in fact, when we eliminate the variable b here, we create a factor over c and d that will be multiplied together when we try to eliminate the variable c. And the variable d, in this case, we have one factor that mentions d and e, and basically this factor here was generated from the elimination process. But there is also this factor here that had the variable f eliminated. So this one here that will also go here. So we can think that is the result of the elimination of f, when we eliminated f from the first step of the algorithm. So we have this new factor here. We're going to eliminate now d. So eliminate d here. We have only the variable e. So there will be a factor only over e that we will need to eliminate this last variable 2, and that ends the process. So these are the clusters that were generated. So we needed to do a little bit of post-processing before creating a join tree with that set of nodes. So it's easy to be convinced that the cluster CIs are sets of nodes from G. And also it's easy to be convinced that the factors in the graph must appear in some cluster CI. So this is just one confirmation for this example that we can put, for instance, this factor here into the cluster C1, these three factors here into the cluster C2, this factor here into the cluster C3, and this factor here into the cluster C4. Actually, those clusters were generated because of those factors, right? So we multiply those factors together in order to eliminate a certain variable. So those factors basically are the domains of the factor that was generated by the multiplication of those factors. So it's easy to understand that each factor will have somewhere to go, one cluster to go, when we finish this process of variable elimination. But we also have these two little guys here. These we call the non-maximal clusters, and we don't need them, right? If we think that, okay, there might be one factor that mentions variable d and e, possibly, but to go here, but in this case, this guy can also go here. So because this is a subset of this. And the same thing for here, right? If you have one factor that only mentions variable e, it's possible, but in this case here, we can also put this factor here. So we don't need these two loss clusters, and I'm going to eliminate them as a post-processing step into the algorithm that generated the clusters. Okay, so we have one property that's very important that is called the running intersection property of the cluster sequence. This property will be very important for us in order to build the join trees later. So this property says that for every cluster I that is not the last cluster, if we take the variables in Ci and make an intersection with all the variables that appear in clusters after Ci, those variables will be contained in some cluster Cj where j is greater than I. So saying that way, it sounds like very complicated, but it's not. It's basically saying that if we take these three variables here that appear in the first cluster, and we make an union of all the variables that appear after the first cluster, we will see that and make an intersection between these two variables. So for here, we're going to see that appears the variables a, b, c, also d and e, and that's all the variables that appear. And when the intersection between d, f, and a, b, c, d, and e, we're going to see that intersection is d. And this de will appear somewhere in a cluster. In this case, it's appearing here and also here together, right, at the same time. Not just d in one cluster and e in the other cluster, but d and e together in a single cluster. And why that's true, it's very simple. When we are working the first cluster here, basically what we are doing is eliminating variable f. When we eliminate the variable f, we create a new factor that mentions d and e, right? And f was eliminated, the factor will be over d and e. So when we try to eliminate d or e in the future, this factor will have to be multiplied by other factors that also mention those variables, and that will naturally create a factor that has d and e and the older variables that came from the older factors that were multiplied by this factor that resulted from the elimination of f. So think about it is eliminating f, create a factor over d and e. This factor will appear later on in the elimination process of these two variables, or d or e. So in this case, it appeared here when we were eliminating c, and we have to put this factor together, and this factor mentioned D and E. All right, so, and that's going to happen for the older one. So let's just switch slides here and see a second case. In this case, we are looking for this cluster here. It came from the elimination of A, so created a factor that mentions BC, and this factor will show up later on when we try to eliminate the B or C, and it's actually happening here when I try to eliminate the variable B. And this is another example. Now here, try to eliminate the variable B. And in this case, I create a new factor that mentions CD. This factor will show up when we try to eliminate C or D, and it's in fact happening here. And all right, so these are the examples, and we have it at the end these two factors here, C5 and C6. There are no maximal clusters. Again, we don't need those factors in order to build the joint tree, so we're going to eliminate those factors. And we need to be a little bit careful when we do this, because we want to keep this running intersection property that we had before. So in order to do this, when we eliminate, we have to change the order of the clusters. Let's think about this in the next slide. Okay, and we have it here in this slide. We have these two non-maximal clusters, C5 and C6, that we would like to eliminate them. And in order to do this, what we do is first we check that they are non-maximal clusters by simply looking if they are a subset of variables from another cluster. So in this case, C5 is a subset of C1. It's also a subset of C4, so we can eliminate C5. But the one problem is that when we eliminate the one cluster, we may lose the running intersection property. And in order to guarantee that we're going to not lose this, we need to reorder the clusters. So there are two examples I'm going to show you. The first one is a little simpler, and the second one will require the reordering of the clusters. So what happens here is that when we have one cluster that's not maximal, we need to find what is the cluster that has the variables of the non-maximal cluster. So if we say that the cluster is C1, and that's true because it has D and E here, so what we do is to remove the C5 and replace it by the cluster that has its variables. So in this case, C1 goes here into the place of C5. Now you may say that is not necessary because this cluster here, C4, is actually guaranteeing the running intersection property because the variables D and E are happening here. So we didn't need to reorder the clusters, and that's true for this example, but there are situations where we lose the running intersection property, and a simple approach to code this is moving this cluster C1, in this case here, to the location of the cluster that is the non-maximal cluster in the sequence. So let's take a look on the next slide to continue to this example. And so in this case here, we move it C1 to this position here, and it is replacing this cluster C5. But we also have this C6 here, and there are clusters that mention variable E. So one is this guy here, and the other one is this guy here. If we replace, if we decide that I'm going to replace this guy here, the best thing that we can do is to move C4 to the C6 position. But in this case, it's also simpler that we just use this guy here, the C1, because the C1 will not need to move position because it will be already the last one in the sequence. That's what happens in the next slide. So we connected C6 to C1 and remove C6, but in this case we don't need to move C1 in position because it's already the last cluster in the sequence. So it ends that way. So we eliminated the cluster. So just a recap here, the algorithm is very simple. We look at every cluster, we take a look if the cluster is not a subset of some previous cluster in the sequence. If it is, we can remove the cluster that is non-maximal and take the other one that is a superset of that cluster into the position of the non-maximal cluster and do that. So it is a very simple algorithm that we don't need to do any other analysis in order to guarantee the running intersection property. So this is a second example. I guess this one is from the book. We have this graph here and we have this elimination order A, B, C, D, and E. So we start eliminating A, and this will generate a cluster that mentions A, C, and D. They are together, and we eliminated the variable A and goes to the next step. Now we're going to eliminate variable B, and B has a single neighbor, so the cluster is going to be BC. And we're going to eliminate the variable C that has a single neighbor. The cluster is CD. Eliminated the variable D, single neighbor, DE, and we ended up with just the variable E that we're going to eliminate in the last step is a cluster over E. So in general, the algorithm that we use to remove the non-maximal clusters is to look at each cluster and compare with the previous ones. If the current cluster is a subset of any previous clusters, we eliminated that. And so we start here in the second cluster. We check to see if it is a subset of the first one. It's not, so there is nothing to do here. But this guy here is a subset of C1. So we can eliminate the cluster C3. But when we do this, we lose the run intersection property. Take a look that in the first step here, we're going to eliminate A. So we have a factor that mentions CD, and this factor was only mentioned in cluster C3. If we eliminate C3, we lose the run intersection property. So in order to guarantee the run intersection property, what we do is a simple approach. We eliminate C3 and move C1 to the position of C3 here. And what's happening here? So because now we did that, when we look at this cluster C1 intersection with everything that goes after C1, there are these two clusters here, it only mentions the variable D. So in this case here, the variable D is the only one that appears in the last two clusters, and it is contained in the cluster C4. So we still have the run intersection property. And in the last step, we see that this guy here is not a subset of anyone that came before, and this guy here is a subset of the C4. So we're going to eliminate this last cluster here. In this case, we eliminate and put C4 in the place of C5, but C4 is going to be already the last one, so there is no need to move it. So we end with this sequence here. So when we have this sequence, it's like eliminating more than one variable at a time. So if we see here, this first cluster here is going to be the elimination of B, and C will show up in some other cluster that is C1 here. And when we look at this, it's like having two eliminations at the same time. We're going to eliminate the variables A and C in a single step, and the variable D will need to show up in a future cluster, and it actually happens in C4. So this is going to be our final sequence of clusters, and we're going to use this sequence here in order to build the join tree. So this is the algorithm for assembling the join tree. It's going to take as input the cluster sequence that only have maximal clusters that were generated from one elimination order pi, and we're going to start with our join tree with the last cluster. So this is the last cluster that we have, and we're going to include this. I'm going to reverse the order here just to make it a little bit more organized. So it's going to be the first node of our join tree. We're now going to process all the remaining clusters backwards. So we're going to start with this cluster here and move towards the first cluster. The idea here is that each one of those clusters, they represent some variable that was eliminated, and the remaining variables that were not eliminated in the cluster must appear in some other cluster after this cluster. So basically what's going on here is that when we process the cluster C3, remember that this cluster was involved in the elimination of C, So DE will show up in some other cluster after 3, and in this case it's actually showing up here in cluster 4. This is what we call the running intersection property. So we're going to connect C3 to C4. So C3 and C4 are connected. We move on, and we go to this guy here, the cluster C2. Again, this was the elimination of B, so CD must show up in some other cluster after C2. It's actually showing up here at C3. And so we're going to connect C2 to C3. So C2 goes connected to C3. And the last one, that is the first cluster, is the elimination of A. So B and C must appear in some other cluster, and it's actually happening here in C2. So we can connect ABC with BCD. And this is our join tree. In this case, here's just a sequence of nodes. It doesn't need to be like this, but this sequence of nodes is the tree. So it is an undirected graph with no cycles, so it's guaranteed to be a tree. But it doesn't need to be that way. We could create some other structures that are not linear like this one, and I'm going to show you one example when that happens. But this is basically the algorithm for building. It's the first one. We're going to also discuss another one based on the maximum spanning tree. So basically this is a step-by-step sequence. So a little bit more organizing than my writing here. So that shows the connection between 3 and 4, and the connections of the nodes C2 and C3, and finding the connections between the connection between the node C1 and C2. So I think that is good for this video. We're going to continue in the next one, where we're going to discuss a second strategy for assembling the tree. Again, we're going to reuse the maximal sequence of clusters, and but in a different way to build the tree. See you soon.